All right, everyone, we are back and we are going to do our lecture 2, t-test, p-values, and hypothesis testing. So we've mastered, and you are all experts of, if you have a PDF and a Gaussian function, how do you find essentially the percent of data that fall between bounds x1 and x2? You can figure out confidence intervals, you can figure out probabilities, and all of that good stuff. However, to utilize this, we have to assume that we know that the population is a Gaussian and is characterized by that population mean and that population standard deviation. But the reality is, when we're doing an experiment or when we're measuring data, we don't really know what that underlying population distribution is. So we don't know if it's Gaussian. There's not a real clear way to establish that, especially when you're doing new experiments. So how can we make that assumption, and how do we actually get to the heart of performing statistical analysis without having to make that assumption? Well, there's a fantastic theorem that we're going to invoke, which is the central limit theorem. So we've looked at the values around a sample, but we need to figure out, we want to basically estimate what is the true mean of the population standard deviation. So for example, I think this is always a good kind of idea that we kind of know inherently, but it's good to visualize. Let's say that we have a bag of marbles, and we see here, it's a bag, the mean is centered around 10, standard deviation of 1, population standard deviation. If we look at this, we can see the histogram, the distribution of those basically marble diameter sizes. So we know if we took the total mean, this would be our population mean, this would be our population standard deviation for this particular random kind of sample, or random population that we basically determine. That's 10 to the 4 basically marbles. If I pull out one marble, this is not a good approximation of the population mean. But if I do pull out 50, let's say pull out 50 marbles, and I start to calculate, let's do mean of that. Now we're getting closer. And if I do, 500, let's actually 500. Let's look at the mean here. I start to get a better and better and a closer and closer approximation, basically to that sample. So I can do here and then here as well. So I'm getting closer and closer to what my real population mean is. So that's the whole idea of essentially why we do multiple measurements. So we're trying to get an approximation of this population mean, of the true mean. So how do we do this? And how do we deal with this idea of we don't want to deal with that underlying population distribution? Well, the central limit theorem is basically this key idea that if we look at the distribution of the means, once we get to large sample sizes of the means, that distribution will look Gaussian. So and I think the best way to kind of visualize that, and we can make this basically a kind of a substitution where we can look at, instead of the population standard deviation, we can redefine, and we want to look at the standard deviation of the means of our measurement, and we can write it in this form and substitute it in, and we can and as you can see here, we can substitute that in for z here, and then you can rewrite essentially the true population mean will essentially be this. And we can approximate here that the standard deviation is just the standard deviation of our means. This should be a hat bar here, and it's kind of the same thing we see here. So this is the key idea. Actually, that definitely has to be a hat. So, and then we can rewrite our sample. Now, I went through that quickly. We see the derivations, but let's kind of visualize this. I think it's really important. So let's say I'm working with a sample that is a uniform distribution. I'm going to zoom in a little bit. So uniform distribution is just basically, I'm generating a random number from 1 to 10, 500. Let's say 5,000. Let's say 50,000. So if I look at that distribution, it's flat. Makes sense. They're all equally probable. So how do we do statistics and look at, do our typical Gaussian, probabilities with that and use our probability density function? Well, if I start to look at, I'm going to pull out a sample that's six samples long. I'm going to calculate a mean. And what I can do is I can say, well, why don't you do that a couple times? So what I'm going to say, and I'm going to actually get a bigger sample. Let's just say I do now 40. Now, one of the things you may be asking yourself, and it's important to kind of think about here, is I'm looking at means of measurements, right? So think about if you're doing a thermocouple measurement, I would argue if you're getting data like every second from that thermocouple, that's already basically doing some averaging in itself. So every measurement at each second would be an average here. So when you're looking at the distribution of those measurements, it is the distribution of the means itself. So let's just say I look at this and I look at 3 samples, or yeah, three averages. Or let's do 5 averages. You see, it doesn't look really Gaussian. But if I now, let's say I did, and I'm going to do 40, let's just say 50. Let's say I do 10. Well, it's starting to look better. What if I do 30? This looks pretty Gaussian. What if I do 50? That looks very Gaussian. So you see, the power of the central limit theorem is that no matter what the underlying distribution is, so it could be a uniform distribution, it could be a chi-square distribution, it could be a exponential distribution, the distribution of the means will always be Gaussianly distributed. So we can apply these substitutions, specifically that, again, we're going to replace the population standard deviation because we want to look at the standard deviation of the means, and then we're just going to replace it as so. So now the only thing that really changes from our previous definition is that instead of just being proportional to whatever our confidence interval value was times the standard deviation, population standard deviation, it's just an extra 1 over square root of n factor. Which makes sense because as you increase the number of your samples, you get a better approximation of the mean, which is exactly what we said at the very beginning. Fantastic. Now, one of the key ideas here is that it becomes Gaussianly distributed once n is large, meaning n is greater than or equal to 30. We call that a large sample size. What do we do for small sample sizes? Well, we have a different distribution that we're going to employ, which is the student's t-distribution. Basically published under a pseudonym student, actually William Gossett, who worked for Guinness, and basically published it without his company's permission. Very dangerous thing to do. It's very similar in form to this new, basically, z value that we have here, except it's a t, basically, calculation here. The t distribution will approach the z distribution when n is equal to 30. So they roughly converge. You see that there's this kind of new value as well. If you look at the t table, and I'm going to actually switch over here. Switch here. The t table gives you the values of t for certain values of alpha and certain values of nu. That shows r here. It really needs to be nu. It's hard to see. Nu is the degrees of freedom. It's just the number of your samples minus 1. Alpha is very similar to your confidence interval, but you'll hear this is the level of significance. It is equal to confidence interval equals 1 minus alpha. So if I have a significance of this, then if I have a 95% confidence interval, my alpha is equal to 0.05. So that's essentially what we're dealing with here. So if you want to find your t value, you can essentially look up this table depending on your degrees of freedom and depending on basically your level of significance or your confidence interval. So you pick the alpha and then you move down this table. Now, there's a nicer way to do that, and we're going to actually introduce it a little bit later when we start to do calculations. We're going to use our function quantile, which basically says student distribution, which is defining your degrees of freedom here, which is your nu, and then we have to define our alpha, which is our confidence interval. So 1 minus our alpha. So you define student distribution, you define the degrees of freedom here, and then you define your confidence level or confidence interval. Yeah. So that's pretty much it. Next time we're going to get into hypothesis testing, and then we're going to actually apply this to kind of look at whether samples are statistically significant or not and all that good stuff. So see you then. Thanks. Bye.